Section 3.6 talks about the binomial theorem. So let's start with an example here. So we're going to prove that n plus 1 choose k plus 1 is equal to n choose k plus n choose k plus 1. And we're going to do it two different ways. So we're going to do it algebraically first. So algebraically, I'm going to start with my, side over here. So I'll have n choose k plus n choose k plus 1. And I want to say what that's equal to according to the formula. So I have n factorial over k factorial n minus k factorial plus n factorial over k plus 1 factorial, and then n minus the quantity k plus 1. I'm going to distribute that minus, so it becomes a minus 1 factorial. So let's think about these factorials for a second. I want to be able to factor out a common term here. So I'm going to think about this k plus 1 factorial as a k factorial times a k plus 1. And that way I can factor out the k factorials of both of those terms. And now this one's an n minus k minus 1. So that's a little bit smaller than n minus k. So I can think of this guy as an n minus k times that n minus k minus 1 factorial. So I'm going to go ahead and I'm going to factor out my common terms here. So both of these have an n factorial. They both have a k factorial. And they both have an n minus k minus 1 factorial. And then let's think about what's left. So what's left over in the first one, there's nothing on the top, so we'll just put a 1. And on the bottom, I just have that n minus k. And for my second term, again, there's nothing on the top left, so I get a 1. On the bottom, I've got that k plus 1, because I've pulled out the rest of the k factorial. And then my n minus k minus 1 factorial all get pulled out. So if we simplify this fraction down, we're going to get n factorial over k factorial n minus k minus 1 factorial times, I'll get a common denominator here, k plus 1 plus n minus k. And then my common denominator will be n minus k times k plus 1. So then my k's cancel. So I end up with just an n factorial over, let's keep everything the same color here, k factorial n minus k minus 1 factorial. And then I have that n plus 1 on the top, and then the n minus k and the k plus 1 on the bottom. So if I put those together, n factorial times n plus 1 is n plus 1 factorial over k factorial times k plus 1 is a k plus 1 factorial, and then n minus k minus 1 factorial times an n minus k gives you that n minus k factorial. And now we can recognize that that is equal to n plus 1 choose k plus 1, which is what we wanted to show. Right, because n plus 1 minus k plus 1 is just n plus k. N minus k, sorry, I wrote something even different. N minus k, and that's what we have here. All right. Great, so this is true. You can see it algebraically. The other thing we wanted to do, though, was show it combinatorially. So let me move that down just a little bit so we have some space here. What do I mean by combinatorially? So we're going to think about what each side is counting here, and I'm going to say why those things are the same. So that's how a combinatorial proof works. So I know that n plus 1 choose k plus 1 is equal to the number of ways to choose k plus 1 items from n plus 1. Right? So now if I can show that the other expression also is equal to that, then I know that those are equal to each other. So the question I want to ask myself is when I'm choosing, so I'm going to have n plus 1 elements, and I want to choose k plus 1, and I want to ask myself, well, let's put the question first, and then we'll draw the arrows. So we want to ask ourselves, did we choose that first, whatever the first element is? Well, we either did choose it or we didn't choose it. So we have these disjoint sets. If we did choose it, now I need to choose k more items from the n that are left, because I already have that first item. If I didn't, then I still need to choose k plus 1 from the n that are left. So the number of ways to do the top thing is n choose k. The number of ways to do the bottom is n choose k plus 1. And then by our addition principle, we need to add them together, and that'll equal the number of ways to choose k plus 1 things from n plus 1. So that's another completely different way to prove this, and that's called a combinatorial proof, because we showed what each side counted, and those were counting the same things. Okay, so we have this fact here, and let's see what we can find from this fact. So let's say I want to find 3 choose 2, for example. I know that that 3 choose 2 is going to be equal to 2 choose 1 plus 2 choose 2. Okay, so if I know what 2 choose 1 is, and I know what 2 choose 2 is, I can just add those together, and that gives me 3 choose 2. What is 3 choose 1? From this formula, it's going to be 2 choose 0 plus 2 choose 1. So if I have my 2 choose 0 here, and I add 2 choose 0 and 2 choose 1, then I get 3 choose 1. And then if I wanted 3 choose 3, that should be 2 choose 2 plus 2 choose 3. But I know that that's just 0. So I don't really need that one there. And the same thing over here, 3 choose 0, I sort of know that that's just equal to 1. So what am I actually getting here? 2 choose 0, what's that equal to? 2 choose 0 is just 1. There's one way to always choose 0. 2 choose 1, I've got two things, I got to pick one of them. There's two options. 2 choose 2 is just 1, pick both. Then below that, I add those two together. That gives me 3 and 3. So both of these here are 3. And then that's 1 and that's 1. Right? So hopefully what you can see here is in order to build up these next binomial coefficients, so this one would be 4 choose 2, I just take the sum of the two above it, and that's exactly how we build Pascal's triangle. So what we're seeing here is that these entries in Pascal's triangle are exactly the binomial coefficients, exactly the n choose k's. Right? So the way we usually think about building Pascal's triangle is each row starts with a 1, and then the entries are just the sum of the two entries above it. So this 1 is going to be the 1 plus the 0. This is again starting with a 1, and then the 2 is a 1 plus a 1. And then we just end with that 1, or we can think of there being a 0 over here. So we get 1 plus 0. But because these binomial coefficients, these n choose k's, follow the same pattern, where you're getting the new one by adding the 2 diagonally above it, we're going to get exactly those binomial coefficients. So this guy is 4 choose 1. This is 4 choose 2. This is 4 choose 3. This is 4 choose 4. And then, oops, did I miss a number? Oh no, sorry about that. Gotta start with 0. 0, 1. Should have noticed those were not the right numbers. 2, 3, and 4. So if you have Pascal's triangle in front of you, you can just read off those rows to find all of those binomial coefficients. Okay, let's look at one more fact we can notice about these binomial coefficients. So I've got n choose k. That should equal n choose n minus k. So let's check that algebraically. N choose k is just equal to n factorial over k factorial, n minus k factorial. N choose n minus k will be n factorial over denominator factorial times n minus the quantity n minus k factorial. But n minus n plus k is just equal to k. So really that's a k factorial. So these are exactly the same. So this is easy to show algebraically. Now, how do we show it combinatorially? That's when we do that counting argument. So n choose k is the number of ways to choose k items from a set of n. So I've got this set. It has n items. And I'm choosing k of them. But whenever I choose k, I can look, and there's going to be n minus k left over. So choosing n minus k and choosing k are really the same sort of thing. There's going to be the same number of ways to do that, because whenever I've chosen k, I've really left k n minus k unchosen. So from each group of k, we get n minus k left over. So the number of ways to choose k is equal to the number of ways to choose n minus k. So we'd have to be a little bit more rigorous about writing that out, but I think it's important to kind of see what these look like, these arguments. So what does this tell us about Pascal's triangle? Right, here is my 4, choose 1. That should be the same as 4, choose 3. So those two numbers are the same. This is 5, choose 2, and 5, choose 3. Those numbers should be the same, right? So if I draw this line going down the middle of Pascal's triangle, then we should have equal numbers on either side of that line. So I'm symmetric across that vertical axis. So that's something that we can see as well. Okay, so finally we're going to talk about the binomial theorem. So the binomial theorem, I've got it written out here. It says as long as you have a non-negative integer n, then to take this binomial and raise it to the nth power, you're going to use these binomial coefficients, right? So I've been calling them binomial coefficients all along, but the reason they're called binomial coefficients is they're going to come because they come from the coefficients of these binomial expansions. So what does this actually mean? Let me draw a little Pascal's triangle over here. If I have x plus y, just to the first power, right, that's x plus y. So the coefficients here are 1 and 1, and that's coming from this first row of my Pascal's triangle. If I have x plus y squared, we know that's equal to x squared plus 2xy plus y squared. So those coefficients are 1, 2, 1, which is the second row of that Pascal's triangle. If we have x plus y cubed, then I get x cubed plus 3x squared y plus 3xy squared plus y cubed. And so the coefficients there are 1, 3, 3, 1, which is that third row of Pascal's triangle. So when I expand a binomial here, the coefficients of that expansion come from these rows of Pascal's triangle. Okay, so let's prove that. So we're going to prove it two different ways. The first way is sort of an idea about why the coefficients should be related to these choosing operations. So how do I actually multiply a long expression like this? Right? How do I actually multiply x plus y cubed? Usually we think about distributing it out, so I would multiply these two first, and then I would put them all together. But really what we need to do when we multiply is we take one thing from each set. So this guy either gives me an x or a y. This one gives me an x or a y. And this one gives me an x or a y. Right, so if I think about that, drawing a tree diagram, I'm going to get an x or a y from the first one, an x or a y from the second one, and then an x or a y from the third one. And then what we do is we're going to multiply all of those things together. So I get an x cubed, and then an x squared y, and then I'll get an x times y times x, so that's also an x squared y. And then I get an x y squared, a y x squared, a y squared x, a y squared x, and then a y cubed. And then I'll just put all of these terms together. So I've got one x squared, I've got x squared y, and then another x squared y. So I have three of those. I have xy squared, three of those. And then finally I have my y cubed. Right, so that's the way that we can think about multiplying this out. So I ask myself, how many x cubes do I have? Well, there were three choices of x, and I needed to choose that every time. Right, so it's actually going to be easier in this case if I focus on the y's. So an x cubed is the same as an x cubed y to the 0. So there were three y's, and I didn't want to choose any of them. So of the three y's, I chose 0, and that's what gave me a y to the 0. And then because I didn't choose any of the y's, I was left over with 3 x's. Now I want to think about how many x squared y's do I get. Here I want to choose just one y. So I can either choose this one, or this one, or this one. So there's 3, and I'm just choosing one. And then if I don't choose the y, I get left over with x, so the other two become x. And then I could also have an xy squared. So here I need to choose 2 y's. So I'm going to choose, of these 3, I choose 2. And there's 3 choose 2 ways to do that. And then finally, for my last term, y cubed, I need to choose 3 y's. So I have 3, I choose 3. Right? And that's exactly what the binomial theorem is telling us. Now we can also see that the same thing is going to be true using an inductive argument, so we'll do that on the next slide. Alright, this induction proof is a little rough, so definitely bear with me here. I'll pause the video a few times so that I can write some things in, and if you ever need a second to catch up, you can also go ahead and pause. So we're going to start with our base case. Maybe we'll say up here, right, we'll proceed by induction. And the base case is when n equals 1, because it says it works for a non-negative integer. So the smallest non-negative is n equals 0. So let's try that. When n equals 0, I have x plus y to the 0. Anything to the 0 is equal to 1. And here I have to think about what this is going to look like. I get a 0, choose 0 times x to the 0. And then none of these other ones are valid because I'm just going to start and end with 0 here because it usually stops at n, and that is my 0. 0 choose 0 is 1. Right, 0 factorial over 0 factorial, 0 factorial. And then x to the 0 is 1. So both are 1. So our base case holds. Okay, so let's try our inductive step here. I'm going to assume, for my inductive step, that x plus y to the n is equal to n choose 0, x to the n, plus n choose 1, x to the n minus 1, y, plus all the way down to n choose n minus 1, x, y to the n minus 1, plus n choose n, y to the n. Okay, so that's my inductive hypothesis. And now I want to show, and I'm actually going to go ahead and write out what I want to show, that when I have the n plus first one, so x plus y to the n plus 1, then all of these n's become n plus 1's, and I get the same expression. Okay, so that's my goal, is to end up with this. So what am I going to do? I'm going to start with my one side of my want to show. I'm going to say what that's definitely equal to, and we're going to hope that we can make it look like that. So I have an x plus y to the n plus 1. So I know that I can say something about what happens for x plus y to the n. So let's pull that x plus y to the n off, and then I just need to multiply that by an additional x plus y. Now by my inductive hypothesis, x plus y to the n is this really long expression here. You might be beneficial to write that out in the sigma notation or sum notation, but I'm not going to do that. I'm just going to go for it and write it out as sum of a bunch of terms here. Dot, 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 plus n minus 1, x to the n minus 1, plus n x, y to the n. And then that has to be multiplied by x plus y. Okay, so now how do I multiply it by x plus y? First, I'm going to multiply every single term by x. So that's going to be equal to n choose 0, x to the n. I'm multiplying it by x, so I get an extra x there. Plus n choose 1. This one's going to be kind of hard to write, but I'll write it as an x to the n, because it's an x to the n minus 1 times that x. But I still have that one copy of y there, all the way down to n minus 1, x to the squared now, y to the n minus 1, plus n choose n, x, y to the n. So everything got an extra x in it. And now I also need to distribute the y's as well. So I'm going to multiply y times this term. And I'm going to actually line it up so it's underneath the term that has the same power. So that's an n choose 0, x to the n, y, plus, then we'll have that n choose 1, x to the n minus 1, y squared, all the way down. If I look at these last couple of terms, y times this guy is going to be an n minus 1, x to the y to the n, plus n, y to the n plus 1. And now we're going to add those two together. And let's see what we get. N choose 0, that's just 1. So that's just the same as x to the n plus 1. And maybe we'll change that in a minute. And now here I have n choose 1 plus n choose 0. But from our original fact, we've seen that, right, that's the sum of those two binomial coefficients. That's the same as n plus 1, choose 1. So I have an n plus 1 choose 1 times x to the ny. And then next I'm going to have just that n plus 1 choose 2 times x to the n minus 1 y squared, all the way down, these two add together to an n plus 1. Choose n, x, y to the n, and then n, choose n, that's just 1, x to the n plus 1. But now, right, what was I trying to show? I was trying to show this expression, which is basically what I have, except that I need an n plus 1, choose n plus 1 here, and an n plus 1, choose 0 there. But I can do that, right? Because I could just say, note that n, choose 0 is equal to n plus 1, choose 0, because those are both equal to 1. And the same thing with n, choose n is equal to n plus 1, choose n plus 1, because those are both equal to 1. So this is what I wanted to show. So I can conclude by induction that the binomial theorem holds. I feel like this proof is definitely less satisfying, less illustrative than the previous one, because it's like, oh, well, I guess we just moved stuff around and made it work. Right? The other one, we were like, okay, it kind of makes sense because I'm choosing the x's and I'm choosing the y's. But this is a little more rigorous because I actually have shown it via induction. Plus, we got to practice with the deductive proof. Now that we've proved the binomial theorem, let's see it in action in a few different ways. So if I'm trying to take this to a high power, I always just go ahead and redraw out my Pascal's triangle. Here I'm trying to take this to the 5th power, so I need the 5th row of Pascal's triangle in order to do that. Kind of ran off the page there, but we got it. So then what do? I take these numbers as my coefficients, so 1, 5, 10, 10, 4, 1. And then I start with the x being raised to the maximum power, so x to the 5th, and then I decrease the powers on x as I go over. And I have x to the 0. And then I do the same thing with my other thing, which happens to be a 4, so I'm actually going to have that number. So I'll get 4 to the 5th, but I do that in reverse order. 4 to the 4th, 4 cubed, 4 squared, 4, and then no 4's here, and then I just add those all together. So perhaps I should simplify this a bit, make it look a little nicer. So I get x to the 5th plus 20x to the 4th plus 4 squared is 16 times 10 is 160, x cubed plus, I'll just write this as 4 cubed times 10 x squared, or you could, well, multiply it out, 4 to the 4th times 5x plus 4 to the 5th. So I can quickly evaluate the expansion of that binomial using my binomial theorem. Okay, so this next one is sort of a strange example. It's asking us what 2 minus 1 to the n is. So we know that 2 minus 1 is just equal to 1. So that's just 1 to the n, which is just equal to 1. So certainly this is just equal to 1. But if we think about it in terms of the binomial theorem, maybe we can get another interesting identity. So what's this going to look like? I'm going to have a 2 to the n, and then a 2 to the n minus 1, and then a 2 to the n minus 2, and so forth. And then here, I have to think of this as adding on something. So it's like I'm adding on a negative 1. So I'll also have a negative 1 to the 0, a negative 1 to the n, negative 1 to the 1, negative 1 to the 2, and so forth. And then we'll keep going down till we get 2, and then just 1 for that 2. And I'll have negative 1 to the n, negative 1 to the n minus 1. So what is this doing here? Well, sorry, let's go ahead and put in our binomial coefficients as well, just so we have everything. So n choose 0, n choose 1, n choose 2, and so forth. N choose n minus 1, n choose n. So I'm taking my binomial coefficients, I'm multiplying them by powers of 2, And then this negative 1 to the n, sometimes it's going to be just a positive 1. And sometimes it's going to be a negative 1. So I get n choose 0 times 2 to the n minus n choose 1 times 2 to the n minus 1 plus n choose 2 to the n minus 2 minus n choose 3 2 to the n minus 3, and so forth. That alternating sum should always equal 1 because we knew it was 1 up here. So let's try that. I'm going to pick a row of Pascal's triangle to find my binomial coefficients. I'm going to put in my powers of 2. So this guy gets a 2 to the 0. This guy gets a 2 to the 1. This guy gets a 2 squared. And this guy gets a 2 cubed. And then I'm going to do an alternating sum, minus, plus, minus. And that should always give me 1. So let's check. I get 8 minus 4 times 3 is 12, plus 6 minus 1. Negative 4 plus 6 is 2, minus 1 is 1. So that's sort of a really weird property of Pascal's triangle that we were able to prove using the binomial theorem. That if you put in these powers of 2 times those coefficients and then do an alternating sum, you always get 1. So we'll finish with a discussion question here. So I want you to show that when the sum from k equals 0 to n of the binomial coefficients, so if you just add along a row here, you always get 2 to the n. So see if you can do a proof like we did in that last problem. So let's just check that it works first. If I add 1, 1 plus 1, 2, 1 plus 2 plus 1, 4, 1, 3, 3, 1, 8. This one adds to 16, right? So those are just my powers of 2. I want you to see if you can prove that fact using the binomial theorem.